Thanks for watching my video. In this presentation, I will introduce my work accepted by ICCV-2025. The title is Reminiscence Attack on Residuals, Exploiting Approximate Machine Learning for Privacy. I'm the presenter Yaxin Xiao. Firstly, let me introduce the concept of machine learning and approximate machine learning. Machine learning refers to a process where the trained model converts to a state as if it was never trained on those data required for deletion. So to achieve machine learning, there are two types of technologies. The first is called exact unlearning, which retrains the models from scratch on the training dataset without any forgotten data. And the other technology is called approximate machine learning. It just adjusts the pre-trained model's parameters to mimic the retraining models. So unlike exact unlearning, it achieves near retraining performance with far less cost. However, it may cause hidden residues of the forgotten data, which can cause the privacy leakage risks. So the motivation of this work is to investigate the privacy concern. Does approximate machine learning truly erase forgotten data, or does it have leave residues that can still leak privacy? While prior studies focused on output space difference between unlearned and retrained models, this paper identifies the latent residues in the loss landscapes. The residues may act as invisible fingerprints of forgotten data, which can cause a new attack surface beyond output-based privacy leakage. So what's residues look like? We visualize the residue in the model's loss landscape, just like this figure shows. It describes two unlearning scenarios. The first is class-wise unlearning, the second is sample-wise unlearning. So briefly speaking, the residues can be understood as the difference between the loss landscapes of unlearned models and the loss landscapes are calculated with respect to the unlearned samples and the out of distribution samples. So we want to see the difference of the loss landscapes calculated on the two different types samples. If they are different, we can leverage such difference to perform membership inference attack. So as shown in the figure, for the unlearned data, actually, the unlearned model's loss surface is quite closer to the optimal region, where the loss is quite small and the color is bright, which means the model still remembers how to learn the unlearned data again. With such inspiration, we propose a new membership inference attack which try to leverage the residues. It's called remnants attack. It can work in both class-wise and sample-wise unlearning scenarios. In class-wise unlearning, remnants attacks measures how quickly the model recovers when retrained on a candidate class. So if it's abnormally quick, then it can be inferred as unlearned classes. In the sample-wise unlearning, Reminiscence attack fine-tunes the model on the retrained data instead of a set of samples, because the samples in this scenario do not share the membership information, so the model is fine-tuned on the retained data, which is pseudo in practice. If the accuracy on certain samples increase abnormally, but such samples are never introduced in this fine-tuning process, then those samples will be inferred as unlearned samples. As an outcome, such Reminiscence attack achieves up to 1.9 times higher attack accuracy compared to prior methods like LIRA or like EOP, which means it effectively reveals price leakage even when the output space is very similar between the unlearned model and the retrained model. Here, this figure shows the comprehensive results of price leakage evaluation conducted by Reminiscence attacks. It compares 12 approximate machine learning algorithms, and we can draw such conclusions. While most approximate machine learning do have very similar output performance to the retrained ones, they show significant privacy leakage when attacked by Reminiscence attacks. In some situations, the Reminiscence attacks can achieve up to 90% attack accuracy. So it means we need approximate machine learning to scrub such price leakage urgently. As a result, we are motivated to propose a new approximate machine learning to scrub residuals. It's called orthogonal and replay unlearning. It includes two phases, and such two-phase design is necessary. In the phase 1, it's called orthogonal learning. It enforces orthogonality of representations of those forgotten data to their pre-unlearning representations. In this way, it can scrub the residues of these unlearned samples, especially those unlearned classes, in deep layers. And in the phase 2, OUR fine-tunes the model on the retained set to avoid pseudo convergence. This is quite effective to resist against the Reminiscence attacks mechanisms. This slide shows the ROC results of Reminiscence attacks. It includes two additional privacy attacks, LIRA and EOP, and it represents 3 different unlearning algorithms. From the results, we can see that Reminiscence attack is highly effective at exposing price leakage in approximate unlearning compared to the additional benchmarks, and OUR unlearning successfully neutralizes such leakage, achieving almost the same resilience as the full retraining. And the results on sample-wise tells a very similar story, and the results in concept unlearning in the generation tasks also tells a very similar story, where OUR generalize well. So in conclusion, we propose we observe a phenomenon that Approximate Unlearning leaves residual traces that can expose private information, and the proposed Reminiscence tag effectively reviews such hidden residues and conduct an effective privacy tag. And we introduce OUR Unlearning to remove deep layer residues, and it achieves privacy and utility comparable to full retraining, while maintaining high efficiency. This slide shows the reference used in this presentation, and you can find our full version paper through this QR code. Thanks for your watching.